Hello everyone, and welcome to this webinar. My name is Jose Loyola Fuentes, and I'm a Research and Development Specialist at Hexel. In this presentation, we will review the state-of-the-art methods related to data reconciliation and gross error detection applied to heat exchanging networks. This is a really interesting topic that we at Hexel are continuously investigating in order to improve the quality and reliability of the results.
So first of all, we need to bring out the challenges related to working with measured data. Measured data is a great and a realistic source of information when assessing the state of our asset. However, one issue that we can encounter is the presence of measurement error. That is, the inherent uncertainty that comes with any measured value. A second issue is that other factors can affect the accuracy of our measurements, such as degradation due to environmental conditions or malfunctioning due to wariness of our sensors. Lastly, due to techno-economic limitations, such as the instrumentation costs and equipment upgrade, not all process variables are measured, and this could become a problem when the selection of measured variables is not done properly. Now let us review these challenges in a deeper fashion. When dealing with measurement error, we account for two different types. The first one is the random error, which is mainly caused by random events, such as fluctuations in the environment or equipment. Their magnitude is typically low relative to the measured value, and it is considered to be as inevitable. The second type of measurement error is a so-called systematic or gross error. Its major cause is equipment or sensor malfunctioning, and its magnitude is normally higher than those of random errors, and that is why they pose a significant challenge when dealing with measured data. We can find different subcategories for gross errors when they are related to measurements, as you can see on the plots on the right-hand side. We have measurement bias, measurement drifting, measurement degradation, and also measurement failure. In addition, when gross errors are related to units, such as tanks or heat exchangers, we also account for another category of gross errors that is called process leaks. Now, the presence of missing measurements leads us to a subsequent set of concepts that are key to understand how data reconciliation and gross error detection work. Process variables can be classified according to their feasibility of being estimated. First, unmeasured variables can be classified as observable or non-observable. This concept defines that a variable is said to be observable if it can be estimated by using the measurements and process constraints, where these process constraints can be either steady-state or dynamic ones. Similarly, measured variables can be classified as redundant or non-redundant. This means that when I delete a measurement, if that measurement becomes observable, then we can say that it's redundant. When this does not happen, the variable is said to be non-redundant. This classification of process variables is key to understand the limitations of the data reconciliation and gross error detection problems, since only redundant measured variables are subject to these techniques. In addition, only observable unmeasured variables can be estimated once measured data are reconciled. The importance of this classification also applies when designing sensor networks, as the designer seeks for satisfying the observability condition, or at least to be as close as possible. There are systematic methods available for classifying process variables, and we will mention them later. So given these current challenges, data reconciliation comes as a suitable method that adjusts measured data to satisfy specific process constraints, for example, mass and energy balances. And as a complementary approach, gross error detection allows for the systematic identification of the presence, the type, and the value of these abnormal errors. The advantages of these methods are that they provide more reliable data, as reconciled data are consistent with their process constraints. This leads to a reduction of the propagation of error across further activities, such as the estimation of heat transfer coefficients or any type of economic evaluation. Moreover, gross error detection is able to identify where specific measurements are corrupted by more than just random fluctuations. Now that we are familiar on what data reconciliation deals with, let's talk about the main methods that are available today.